Continuing on our review of exact differential equations, remember we left off the previous discussion with this particular differential equation, which was shown not to be exact. Sometimes equations that are not exact are actually not far away from being in exact form. And what I'd like to show you is that what if you consider this particular equation that we have, which was not exact, and multiplied through by 1 over x, or divided by x through the whole equation. So let's look at that. Suppose we multiplied this whole equation by 1 over x. Go ahead and divide through by that. X will multiply by 1 over x, and what we have then is 1 plus 3 quantity x squared times sine y, all that is times dx, plus of course x cubed cosine y, all times dy equal to 0. Making the assumption, of course, x would never be 0 for this equation. So the question is this exact? Well, of course, here's our new m of xy to test, and this is our new form for n of xy. Right? So to test exactness, remember there's two partials that we want to see if they're equal. You want to see if the partial of the m function there with respect to y would be the same as the partial of n of xy with respect to x. Okay? And so let's just do those very quickly right here. Let's just do that, bring it down. Take this particular x and y combination and take the partial derivative, the partial derivative with respect to y. That means take the derivative with respect to y and hold all x terms constant. Derivative of 1 will be 0. This will be treated as a constant times the sine of y. Derivative of sine is cosine. So then what we would be obtaining is 3x squared, that constant term, times cosine of y. Now come over here. We want to take the partial of this expression x and y with respect to x. That means take derivatives with respect to x. Any y terms are treated as constants. So cosine y is then a constant in this case. So this would be cosine y times what? Taking the derivative of x cubed with respect to x would give you the quantity 3x squared. And lo and behold, those are equal. So therefore, this slightly modified equation from the previous one is exact. So now we can actually solve that. And this time we'll go ahead and solve for this particular equation that is exact using this technique we've just developed. All right. So what I'll do is I'm just going to push my paper up. Let's just start the process again by writing the equation down and proceeding with the solution. So what we've got is this new exact problem is 1 plus the quantity 3x squared sine y dx plus x cubed cosine y dy equals 0. This is our new m of xy terms we said, just repeating what we already had in the notes. This is n of xy. Because it's an exact equation, we know there is a solution of this form. There is some function of x and y equal to a constant that will produce an implicit solution for this exact differential equation. And we know that the function can be obtained to start off with either one of two integrals. We could either get it by the integral of, say, the n term, n of x with respect to y, plus terms in x, which we'll call h of x, or we could proceed by trying to create it from the integral of m of x, y, y dx, plus terms solely in y. This means terms completely in y, not mixed. This is terms completely in x, not mixed. Okay? Either way is fine. What I usually look at is, well, which integral do I want to bother to have to compute? And either one of these turns out to be not too difficult, but because there's only one term here and two terms there, I would go with the first one. I would go with this first form. Okay. So in that particular case, what we'll be writing f of xy as is the integral of x cubed cosine y dy plus terms in x, which will be represented as h of x. But you're integrating with respect to y, so x cubed here will be acting like a constant, so that's going to be x cubed on the integral of cosine y dy. And I think we all know what the integral of cosine is. That's simply equal to sine. So what we really have is the solution to our differential equation has this form. It's of the form x cubed sine y plus terms in h of x, like that, terms in x. Again, you don't have to put a plus c over here because we know ultimately f of xc is going, f of y is going to be set to c, and those constants would just be added or subtracted into the same thing, so we don't need to bother with it at this point. All right. Now, the question is, well, what do you do about this? What other piece of information can we use to figure out what that form would have to be like? Well, since the equation is exact, if we come back up here, one of the conditions that has to hold is that if it's exact, the partial of the solution with respect to x has to be equal to m of xy, and the partial of f of xy with respect to y has to be to the n term, n of xy, right? So what we want to use here is figuring out what h of x is, well, let's take the partial with respect to x. If we were trying to figure g of y, we would use this other partial. Okay? So what we're saying is that I know what the partial of this form with respect to x has to be equal to. It has to be equal to m of xy, which is equal to what the original equation says is 1 plus 3x squared sine y. Again, this came from the original equation. That's what m of xy is. So what we need to do is, well, we think we've got a form for f. Let's take the partial of this and set it equal to this form right here, this expression right here, and see if we can figure out a constraint on the h. So if we do that, bring this down, the partial of f y with respect to x would have to be what? Take the derivative with respect to x, hold y constant. That's going to be 3x squared times the sine of y plus the derivative of h. Remember, partial with respect to x means take derivatives with respect to x, hold y terms constant, but there are no y terms here. So this is just going to be the flat-out derivative. But then pattern matching here, we can see, well, because it's exact, this has to be what the partial of f with respect to x is. And the constraints I've come up above says, look, it's really just h prime of x. So what has to match is that h prime of x has to be equal to 1, which tells me, oh, all h of x really has to be is x. So it's kind of like another integration. It's just a very quick integration to say, well, if the derivative is 1, the antiderivative is x. So therefore, what we've determined very quickly is that f of xy really is just x cubed sine y plus x. And setting that equal to a constant gives us an implicit solution to this exact differential equation.